This is Math 432, Applied Combinatorics. I am Professor Asaf, and today we're going to be coloring a map. So first of all, what's the problem that we're trying to do in the math sense? Given a map of regions, such as the Western United States, how can we color each region so that no two abutting regions have the same color? So what that means is whatever color I choose for New Mexico, I have to choose a different color for Arizona because they share a border. And for the purposes of this map, let's just say that Utah and New Mexico don't share a border since it's sort of a corner there. All right, so let's go ahead and color this. Let's maybe start at the top with Washington. So maybe Washington, we're going to color red. Now, the goal is to use as few colors as possible. Pretend I'm a cartographer and I don't want to pay a lot for paints. So once I color that Washington red, let's go ahead and color Oregon green. Okay. Now, think about what I can do for Idaho. Okay, so Idaho here, it can't be red and it can't be green because it shares a border with both of these. That means I'm going to need 3 colors. Okay. And the question is, how many colors do I really need to finish this out? So there we go. Now, if we think about Montana, we can actually reuse green because no reason not to. I could have used red, but I chose green. Okay, so let's keep going down. Wyoming, what's Wyoming going to be? Well, it looks like I can't use green or blue, so I could use red. So we've got Wyoming. And now if we look at Utah, Utah's got to be green. Again, if the goal is to use as few colors as possible, green is what I've got to do here, which means that I've got to use blue for Colorado. So Colorado is now blue. Great. New Mexico could be lots of different colors, but just to emphasize, I don't care about that corner. Let me just go ahead and do it green. And then I can color Arizona blue. And let's go to Nevada next. Nevada is going to be tricky. Okay, are we in trouble with Nevada? So Nevada is touching Arizona, it's touching Utah, it's touching Idaho, and it's touching Oregon, but those only use, among them, 2 colors. So I can actually go back to red. Great, so Nevada is now colored red. And now we arrive at California. And we see that California is touching Oregon, Nevada, and Arizona. We need a new color. So we're going to have to choose, for example, purple for California. So it turns out for this map, we needed 4 colors. But maybe that was just because the way I did it. We want to ask ourselves, was the reason I needed 4 colors, is it because of the way I colored the map? Did I always need 4 colors? Could I have done it with 3? Are there some maps that might need 5 or 17? How can we think about that? So the solution to this problem is to turn it into a more graph theoretic problem. And we're going to turn this into graph coloring, which we've discussed before. So turn this into a graph coloring problem. So remember, we colored graphs, but how are we going to turn this into a graph? It sort of almost looks like a graph, except I'm coloring faces, not vertices. And there's a great way to switch between that. So here's a definition. If you, given a planar graph, which we can think of a map as, so given a planar graph, now we have a notion of faces. We can create the dual graph. Maybe I'll emphasize the terminology here. The dual graph has, well, it's going to have vertices and edges, so I need to define those. So the vertices are the faces of G. So given a planar graph, which we'll call G, the vertices will be the faces of G. And now when do I have an edge? So an edge from, say, face 1 to face 2, when F1 and F2 have a common edge in G. So how can I think about that for this example? Well, here's my graph. So I can think about putting a dot for every vertex that I see here. So for every vertex I put, for every face, I put a vertex. And I'm going to color the vertices the same color as the faces. And now you can see that what I've got, maybe I'll make another copy of this that's isolated down below. What I end up with is a graph that I've colored. And I've colored it in the usual sense, that I have the vertex coloring and I'm trying to get no monochromatic edge. Because we have an edge between 2 faces whenever they're abutting, this condition of no abutting regions have the same color is really telling me I want a proper coloring of this graph. So the way I've colored this map corresponds to this proper coloring of the corresponding dual graph. So really what I'm asking myself is, okay, well, how do I properly color that? And so here's an important fact. The dual of a map is always a planar graph. So the question that I really want to ask myself, so the problem up at the top really becomes the following. So here's my new problem. What is the chromatic number of a planar graph? So given a planar graph, how many colors do I need to color it? Let's look a little more in depth at this planar graph that's the dual of the Western United States. It turns out that I needed 4 colors in the way that I did it. But did I really? Well, if we look up here, we can see that this isn't going to be a bipartite graph. We're definitely going to need at least 3 colors because I have a triangle. So remember that a triangle is always going to force me to have 3 colors. And similarly, I think it's important to note, as an important example, K4, this is planar and needs 4 colors. You have to do each of the 4 vertices of K4 a different color, right? Because they're all connected. So we know that the chromatic number of a planar graph is at least 4. So we know that chi of G is greater than or equal to 4. Well, not for every planar graph. Some don't need that. But most planar graphs are going to need at least 4 colors. So we want to know, okay, well, can we do it with 5 colors? Can we do it with 6 colors? Some graphs need 17 colors. So still looking here at this example, we see that we need at least 3, but did we really need 4? Well, I don't see a copy of K4 anywhere. You'll see that I had to curve this line around, and that idea of having to do that curved line, I did straight lines here, so that tells me there's no K4 in here. So did I really need 4 colors? Well, the answer is Nevada. Look at Nevada for a second. If we go around Nevada this way, I've got a cycle. So there's a 5 cycle around Nevada. And the 5 cycle needs 3 colors, right? It's an odd cycle. Odd cycles need 3 colors. So I need 3 colors for all of these states that border Nevada. And Nevada itself touches each and every one of them, which means I need a 4th color. We need a 4th color for Nevada. So definitely I could not have done this graph in fewer than 4 colors. But are there other graphs? We can see how even though I didn't have a copy of K4, I needed 4 colors. So even though K5 is not planar, I'll never get in a planar graph, I'll never get K5 because that was a theorem from last time. But maybe I'll still need 5 colors. It could come up with that situation. And that's what we want to think about. How can we reduce this problem and how can we get it down to some sort of theorem where we say that, well, this many colors is definitely enough?